I'd like to talk about today, this afternoon, is various maybe let's make a little joke. Children of the Riemann curvature tensor. So, children, if you're a father, you're not a father or a mother yet, but I don't think. But usually the children at first don't know as much as the parents. Later on they know more. I've experienced both phenomena. So, in other words, given the Riemann curvature tensor, we deduce other curvature notions, which maybe are more intuitive or maybe simpler to understand. So the two notions that I wanted to first speak about are called sectional curvature and Ricci curvature. So first, sectional curvature. Well, let's call it A, and let's call it B. Well, the idea of sectional curvature is cut M is given to us with a Riemannian metric, say. So let's start our situation with M, G to be Riemannian, and from now on, I think today, this afternoon, or maybe this afternoon, I will always have the Riemannian situation. So the vector bundle in question is a tangent bundle. The idea is to cut M in surfaces so M's high dimensional. M may be 100 dimensional. And somehow or another we want to cut it in surfaces as pi. And somehow pi will be parameterizing the surfaces. I'm using classical notation here. It would be a parameter of the surface. So pi will be moving somehow. So we'll cut M in surfaces. So I'll draw a picture here. And somehow cut N in a surface as pi. This will be two-dimensional. Maybe M is 100 dimensional, and we cut it in surfaces, say through a base point, but we cut it in many surfaces. Okay, so all possible surfaces somehow, and then compute the Gaussian curvature of each surface, and that will be somehow a measure of what we call sectional curvature. The word section is a cut. So the question is how do you find these surfaces? These various surfaces. Okay. And what we do to find these surfaces so-called exponential mapping. So the answer to this question is use the exponential method. Whatever that is. So, as you know, e to the x or e to the z or e to anything is really an important function. And here we have also the exponential function, mapping. And let me draw the standard picture that you should keep in mind. Of a sphere. So this is what Gauss had in mind, of course. So you have a sphere, and you have a point in the sphere. So we're cutting through a point P. We're fixing a point P and looking at all these surfaces through P. And by the way, they'll be local surfaces. They won't be great big surfaces. Just they won't be closed big manifolds. They'll be just a local thing. And here's the way you see how to do it. Well, at least here's the exponential map. Let's see here. So I hope you can visualize this. Here's the North Pole, and here are all the glaciers melting. And here is, this is the tangent space to the North Pole. So let's say that point is P. This is the tangent space to the P of the manifold. Right? And the picture that you can imagine is that if you take the tangent space of the manifold, you should be able to, and you take a line here, that you should, a line in this tangent space, you should be able, I'll try to make it, you should be able to push that line down to a geodesic, so that you have this line down, and you should be able to push this line down to a geodesic in the manifold. Right? You should be able to do that. And then you take another line, and then you will be able to push it down to another geodesic. So you see that picture, you can imagine, well, you know what the geodesics are of the sphere. So it makes sense, right? You have these geodesics, and they are somehow parameterized by lines in the tangent space. So this mapping from the tangent space to the manifold, I'm going to make precise in a second. It may be not well defined everywhere, but it's in principle you want to try to have a map from the tangent space to the manifold. And the idea is to take a line and map it down into the geodesic of that line. Right? Okay. Now there are a number of bad things that can happen. If the manifold is compact, as you know, the geodesics exist for all of time, or if it's complete. So in fact, this picture might even be right. You take a complete global line all the way out to infinity, and you can map it down to a global geodesic. Right? I mean, you see that with the Earth, right? I mean, you can take that line there and map it down to this geodesic. Something like that. Right? Actually, you want to be a little bit careful, because geodesics go forward. So really what you're doing is you're going out along this, which line was it? This one. You go out along this line in this direction, and then you go along this, it's a curve which is parameterized by arc length, and it goes like this. So really what you have is you have two ways. You go along in a positive time that way, and you go along in positive time this way. Right? So in some sense it looks like that. Right? That's what it looks like in terms of, yeah. So, okay. So, how do you define that? Well, that's a standard dynamical system. So we have the tangent space. So we have V in the tangent space at the point P. And you say, well, what I'm going to do is, I'm going to look, that's a tangent vector. That's a tangent vector. And that's a tangent vector, and that's a base point. So those are the two ingredients, a tangent vector and a base point. Right? So those are the initial conditions of the Euler-Lagrange equation. Right? The initial conditions is the point and the velocity. and then you get the geodesic of the Euler-Lagrange equation, right? So the trouble is, as you know, this thing might only be defined for a finite time, right? Because, okay, if it's compacted, so it's for infinite time, but it might only be time. So somehow we take v to be small. Okay? So what does it mean v to be small? Well, it's pretty clear. We have the tangent space. This is tangent space. Here's 0, the tangent space. Here's the tangent space. So what does it mean to be small? We have a metric on this thing, g. So we mean small in this norm. Right? So if v is small enough, then for sure you're going to be able to integrate this thing for time 1. Right? If v is small enough, you're going to be able to integrate this thing for time 1. Right? So v to be small, then it implies that g, t, v exists for t less than, or say for t starting at 0, because that's the way we look at it, less than some number epsilon, where epsilon is greater than 1. Right? If I take t small enough, right? You look mystified, but you okay on this?
I'm not sure what G is.
T is the
G.
if you have a local group action, which we have for the Euler-Lagrange equation, you have the one-parameter groups locally, g, t of v. T is time.
Okay.
Okay. So, as we know, this may not exist for infinite time. However, right, for v small enough, we can take this to, you see, I can make v smaller or t, and when I make v smaller, I make t bigger. Right? You see what I'm saying? So, if I take v small enough, then inside some ball of radius, so let's say norm of v to be, the g norm would be less than some small radius, then then this thing exists for all epsilon up to 1. You get it? You certainly get it. If I fix v, then I can make it smaller and smaller and smaller, and this is going to be true. And now you understand what I have to do here. I have to use compactness. This is true for each v, right? For each v in the direction, so that's on a compact sphere, and right? And I use the compactness of the sphere, and so that if v is small enough, then this thing exists for all v. Okay. So then I have to define xp of v to be the time equals the time 1 of, well, I'll write it here. G t based on v of p for t equal 1. Time 1 flow. You get it? If v is small, if v is big, I'm in bad trouble. Right? I take time, if v is too big, I can only get time 1/2. Now I'm going to make v smaller, and now I can get time 1. Right? Okay. So that's called the exponential method. Okay? Now there's several problems. The first problem is this problem. You go out here in this direction. You go out here. Oh, you go out here. What is the image of at p? This is p0. P. What is this thing? The zero goes to p here. 0 in the tangent space gets mapped down to p. So this is 0 in the tangent space, this is t in the manifold. So, okay, so here is V here. What's the differential of the mapping in this direction? It's V, right? That's the velocity. That's the velocity of that flow. So we restrict it to this line here in the tangent space, and the mapping is just this thing here, and its initial velocity is V. That's the ODE. Its initial velocity is V on the ODE. Okay. That says that the differential, that xp star at 0 is the identity. Right? Because at each thing I go, the tangent vector that I get is simply V. That's the velocity vector here. That's the velocity vector there. That's whatever the velocity is. That's it. That's V. So the picture is this, that it's the identity at 0, because along each thing it's V. And then in particular that says for maybe taking R perhaps smaller, taking R perhaps smaller, this mapping maps the ball of radius R around 0 diffeomorphically onto a neighborhood U, which is a neighborhood of the point P in the manifold. Get it? Shall we go through it again? Yeah. You have a one parameter group orbit, local. Right? At the beginning, its initial conditions are the point and the vector, the initial velocity vector. That means this mapping of the interval, starting at 0 and following time, this means that the initial velocity there is from the interval that's parameterizing this, is that vector. That means the differential of that map is the identity, right? So that's true for each line, and so the lines pave out all directions. So that says the differential of this mapping here is the identity at 0, and if the differential is the identity, the map is a diffeomorphism locally, and I just take a small ball and small enough ball so it's a diffeomorphism, and I have that. Okay. Now that's a wonderful thing in my mind, because you have beautiful coordinates here, which we call normal coordinates. This picture here, I'll make it here on the board in the orange picture. That's going to be the North Pole here, P, and we have these wonderful coordinates, which are effectively intervals like this in the tangent space. Right? This is a dynamical system. It couldn't be better. We have linearized it, so it is just this beautiful, beautiful thing, right? Cannot be better. So this is called normal coordinates. Okay. How could you not look happy? What's bothering you?
So the explanation map goes from the tangent space at a point to the manifold, right?
That's right.
And the way you do it is that you pick a vector in the tangent space, and that gives you some sort of one parameter group action or whatever on the manifold.
Right.
I kind of lost you after that.
Okay, that gives you, and now you take the one parameter group.
Yes.
The first remark is that's very dangerous because it might not exist for a very big time.
Yes.
However, if I take the same vector, only I scrunch it back smaller, it's going to exist for time 1 or more. That's what I want to get at least to time 1. Okay? So I take the vector small enough so that the time one map is defined. We call it the time one map of the dynamical system. Okay? The time one map is defined, and now for every vector. And of course, the initial velocity tells you what the differential of that map is, so that says the map is the differential is the identity. At zero is the identity. Right? So it's a diffeomorphism. So I just have, all sorts of things could happen. The geodesics, if you take them too big, they intersect. We know that on the Earth. By the way, where they intersect has a name. It's called the cut point locus. So that can happen. All sorts of terrible things can happen. But locally, it's a diffeomorphism. And so the local picture is precisely that. Yeah? And by the way, you can also see that you also have polar coordinates. You really see this if you think this is the circle and this is just a radius. But of course, in general, that's a sphere and that's a radius, so it's just polar coordinates. Any physicist knows that. Okay, so you have local normal coordinates, or what are called polar coordinates, and this is a set. Okay? I think we're okay on that. Do you think it's okay? That's the standard thing. And now, well, here's going to be this, what did I call it, the section. So how find the section now? Find the section, which will be parameterized by some number pi, or whatever it is. It's not even going to be a number, it's going to be something else. It's going to be, okay? Where pi is a two-plane in the tangent space. I'm going to find the section. Okay. Well, that's not very hard. I just go here. I'll draw you a picture of it. Here's the tangent. Here is the tangent space at a point, as if it would be three-dimensional. It would be the tangent. Here's 0. This might be the tangent space at P. Here's 0. This is the relevant thing at P. And then I take a plane. When I say plane, I always mean the subspace. I don't mean some affine plane far away. Okay, I mean subspace. So I take a plane, and this plane in Gauss and everybody notation is called pi. So in this thing, we have a plane. We have a plane called pi. A plane called pi. Okay. Now, of course, this plane is a great big plane, and this normal coordinates only exist for a neighborhood. So there's a ball in there of radius r. I'll draw it wrong. I draw it some other color. I don't know. Oh, here. So I'll draw a ball in here. This is a ball in here, and it intersects this plane. This is the ball. This is the ball of radius r for normal coordinates. This ball of radius r, and it cuts this thing in a sphere. The ball cuts a plane in a sphere, right? Plane in a disk, right? Well, so we have the let's say so I take P. So let BR be is around 0, B as above. And maybe PR equal BR intersect P, where P is a two-plane. P is a two-plane. Okay? I got it. And now I'm going to SP equals X of PR. You got it? Right? I just take a plane, and the picture is a stupid picture. You have a great big manifold, and I have a plane, and in this plane I have a disk filled out by lines, and these lines go down a geodesic. You're okay on that. That's the way it works. Okay, so that's a beautiful thing. And this is a local, what I call a local section. So it's a local surf. So we have this manifold now, which is a huge manifold of dimension 5,080. And here's a point we're discussing. And at that point, we have a piece. It's just a piece because we can't judge how big everything's going to be. This is going to be SP. I've drawn it as a curve, but it's two-dimensional. Okay? No problem. I think you're okay. It's very simple, right? Okay. Now, Gauss told us what to do. Gauss said, compute the Gauss curvature of SP. Why not? Okay. And now, I made some remarks this morning. I hope you remember maybe some of my remarks. Was it depends how you define nabla. You can have nabla, which is defined by the ambient nabla or by the intrinsic nabla, right? Let's recall that. So let's recall the problem. The problem is you take x and y, vector fields. I'll write it in the notation here that we're dealing with. Vector fields, two vector fields which span the tangent space to SP at P. Okay. Those are two vector fields which span that thing. Extend these things to x and y as vector fields in a neighborhood of P, SP. So that's a local neighborhood. I can extend a little bit. And then, as I said this morning, I think most everybody was here this morning. So you have two things. This morning, as I said, you have nabla tilde, and when I write this tilde, that means that of the extended things. Okay, I could write here x tilde y tilde, but I'm not going to do it. This means you take the extended things, you take the nabla tilde on the ambient space, and then you regard, and look what happens when you restrict back to the manifold. Right? This thing is not this is definitely not necessarily just you take the ambient thing, you take the canonical thing of SP and take it out. It is definitely not. It is definitely not. Gauss knows what the error term is. You wrote pi here for some reason. Pi of x, y. It's called the second fundamental form. Gauss knew that there's not an inequality, right? So the question is, what was the idea? I don't know where I write. What was the idea? Compute the Gauss curvature of this thing. Let's call it kxy, where that means you take two vector fields which span this thing. You take the well. Let's remind ourselves what this thing is. This is something like S x r r x y y x over volume, or in this case, the area, but it's scaled, it's a number. This is the Gaussian curvature of that plane. It's a number. It's well-defined independent of x and y. Okay, it's a number. Yeah, but where in the devil are you talking about? Are you talking about the Riemann curvature tensor of the ambient space or the plane? So it's very dangerous. So it's danger. Danger. Right? You don't know what. So what you have is you have K tilde. That means you compute the Gauss curvature using this guy to define the Riemann tensor. Right? That's one thing you can do. Or you do this guy, which is the intrinsic guy. This has nothing to do with the ambient things. It looks like you really just use a restricted metric here, and you have to see what happens. And guess what? Okay. So a silly calculation proves that, but it's an important thing. Okay. Now, these calculations are in your book, but I have a friend in Sydney, Australia. I like her very much. Her name is Emma Carberry. And she's a beautiful lecturer and writes beautiful notes, and I will send you the notes of her notes on this kind of stuff. And it's not as boring as you might fear. She does an excellent job. Okay. So Emma Carberry's notes. These things are also in the book of Lee. Every calculation I say here is in the book of Lee. But I like her notes better. Okay. And it's not buried in 150 pages of a book. It's 5 pages of notes. Okay. So that's the calculation. That's wonderful. It means somehow you don't have to worry. Okay? So the sectional curvature is a map from the Grassmannian two planes. Sectional curvature, let me say sectional curvature at P is a map from the Grassmannian of two planes in the tangent space at P to the real numbers. So each plane gets a real number, and it takes the plane, and Grassmannian of two planes means the set of all two planes in the tangent space. I call that the Grassmannian. Okay? So this is a compact manifold, by the way, that's very nice that it's a compact manifold. So it's a certain compact manifold. The Grassmannian, it sends a plane to the Gaussian of that plane, and it doesn't matter which x and y you put in here. Okay. Okay. So each plane gets a number. You can visualize this because you might have a saddle point, for example, where it's curved this way at one time and this way at another. And you can imagine as you move around all the planes, things will change. Okay, so this is a non-trivial thing, possibly. Okay, it's called sectional curvature. Okay, you okay on this, Sandy? Okay. And there's some remarks. The first remark is just a notation. When you hear somebody talk about constant curvature, usually they mean constant sectional curvature. It means that this mapping is constant. Okay, that's usually what they mean. Sectional curvature is a constant function. These And there's another remark, and let's call this exclamation point. There's an easy calculation that Emma writes down in a clean way, is we can recover the full Riemannian tensor from sectional curvature. So this means that in reality you don't need to look at this huge, awful tensor. You've cut down the problem to looking at two-dimensional stuff. And so Gauss is very happy because that's essentially what he did all the time. Okay? So you can recover it. There's an explicit formula you can see. So, see her notes, very nice. Okay? So that's sectional curvature. Okay. Now, I hear somebody with a remark, yes.
So the notion of curvature, the Riemannian curvature requires a connection, which is an additional choice that we make. Whereas here it seems that it's some sort of canonical thing, right?
No, it requires a connection. Look.
So how did Gauss go about computing these when he did not know about
How did he go about it? He knew that you had two nablas because he had a surface embedded in R3. One using the intrinsic of the induced metric. So he had a metric. And what he did is this. He takes two vector fields. He computes nabla as if they were in vector fields in R3. Right? And you get nabla of x applied to y, some vector field, but it's not tangent to the surface anymore. Right? That's the problem. So he says, okay, I'm going to understand the tangential part and the orthogonal part using the splitting of the metric. Okay? That's what he did. That's where all his calculations are based around exactly that thing. Okay? And then he was incredibly happy. He called it his theorem something something. I forgot. I don't know the Latin. Somebody, yes, he's very happy. Astonishing theorem that it doesn't matter from the point of view of Gaussian curvature. And he's saying that proves that Gaussian curvature is an intrinsic thing. Well, but he did the whole calculation embedded in R3, so it didn't mean much to me when I first saw that. But it is an intrinsic thing. That's an example of it. Right? Okay? What? Okay. So that's very beautiful, I think. And now there's another notion of curvature we all use. This notion is called Ricci curvature. There's this great Italian school, Ricci and various other people at the same time, very close to the turn of the 19th into the 20th century. And these guys were really good at moving indices up and down and so on. They were masters of this, as was Christoffel and so on. And this was probably discovered in that way. So what do? Well, you look at the Riemann tensor. They knew about the Riemann tensor. That was probably new information implicitly in Gauss's work, but maybe not explicitly. You have Riemann tensor. I'm trying to follow standard notation. Zeta xi of eta. Do you mind if maybe I'll write eta here without?
The first is zeta and the second is...
The first thing is zeta xi, eta. That's my version of zeta.
Yeah, it's very similar.
It's not a bad version. Come on, give me a break. So okay. Okay? Anyway, it's gonna vanish soon. Yeah? You're gonna call this a map of zeta goes to, I'm gonna practice drawing it to make you happy. I'm gonna regard this as a map. Okay? That's a map, right? Zeta goes to this guy, whatever this is, right? It's a map. It's a wonderful map. I take the trace of this map. Okay. The trace of this map. You can imagine how good that is. That kills conjugation and so on. It's a wonderful thing. The trace of this map the map zeta goes to the Riemann tensor zeta c applied to eta is called Ricci. Ricci, and then usually nowadays abbreviated RIC, is called the Ricci curvature of C eta. Okay. Okay. Now, this guy is wonderful. This guy is symmetric. So, Ricci is symmetric. So it's a bilinear guy. It's a bilinear form. You can see in eta, and that implies that knowing the Ricci applied to C, so it's effectively the norm of this symmetric product, is enough. If you know the norm of, you know this formula, right? If you know if you have a bilinear thing, and you know the norm, you can get back the inner product. You know how to do that, right? You take A plus T times B, the norm of A plus TB, and apply and multiply that all out. And if you know the norm, you get the inner product back. Right? So knowing this for in fact for a norm of C squared equal to 1 is enough to know the full Ricci form. So sometimes you will see only a function of one variable, namely the norm. You might call it the Ricci norm. Okay? That's good. And now here, you've lost information. Sectional curvature, you lost no information. I suggest you read the notes of Emma Carberry on that formula. There is a direct formula that from sectional curvature to the full Riemann tensor. Okay. Here you've lost something. So here we have lost information. I always say life is capitalistic, although I don't like to believe that. It goes against my own personal philosophy, but you pay your money and you take your choice. What you've done here, you've lost information. That's the money you paid. But what you've gotten for it is you've gotten a far simpler thing. Okay, you've gotten a bilinear norm. Okay, it's called the Ricci curvature tensor. And now, let me tell you what you've lost. You got a remark? Let me tell you how to think about how much you've lost. Okay? So, deriving Ricci from sectional curvature. sectional curvature gives you everything. You can recover the full Riemann curvature tensor from sectional curvature, but Ricci, you're losing something. Let me tell you what you do. So you take C as a unit vector. Everything is going to be a unit vector. Norm C equals 1. Okay? Okay. And now you extend that to an orthonormal basis, of the an orthonormal basis of orthonormal basis of the tangent space. I hope you understand. I've fixed a base point. I'm discussing this at one base point all the time. Everything depends on the base point. All right? Okay. So an orthonormal basis of this with respect to the metric. Okay. And now, if you have this guy and this guy, you get a plane. Maybe I'll call this plane P2. Because, well, maybe I have to, P2. Okay? And now I have another plane, and this plane, well, I have to take a span here. Span. That's plane P2. And then I take span of C and E3. That's another plane P3. Etc. Right? So I have an orthonormal basis and I get a bunch of planes. Okay? For each plane we have sectional curvature. The Ricci curvature is the sum of those sectional curvatures. Okay? So the Ricci curvature is the sum, can be shown also in her note of the sectional curvature. Of these planes. And in the literature they write, or we write, the average in some sense. In some sense, the average over all these orthogonal planes. So you're losing a lot of information when you do this. You cannot recover at all the full sectional curvature. Okay? And those are the notions of curvature that I want to make sure you've heard about anyway. Okay, any questions about those right now? Start with a connection or a metric Sunday.
What are these planes? These planes. Like these planes you define here, like what are they compared to the sectional plane we took there?
I'm not hearing you, it's my problem. Maria's not here, so I'm not hearing you. What if?
So we define some planes here, right?
Yes,
So we also
in an orthonormal base. I mean, it's fundamental to use an orthonormal basis. Yes.
so we had some sectional plane when we define sectional curvature.
Yes.
So like what are these when what we define here? I just want to get the sense of the planes we define.
I'm not sure what the question is.
So
Again, I have n planes
Mhm.
determined by an orthonormal. I start with a unit vector. Then I do the usual basic extension thing with the metric.
No, I mean like some examples like calculating Ricci flow and some.
Oh, okay, this is a very hard thing. So he would like an example.
Yeah.
Okay. Okay. And as well, there will be good I will give you good examples, but that's the problem with the subject. It's every example, if you don't have any technology, every example is non-trivial. Okay? Every example is non-trivial. Okay? So I will come to some examples. As you notice, I've given no examples in this course. I don't know if you noticed, except for more or less trivial things. Every example in the subject is non-trivial. I mean, you took it in one of your questions, you took a torus sitting in R3, right? I'm not sure you did that right, but that's already a slightly non-trivial example, right? So I'm going to show you more and more how to compute examples, but with general technology, not with some, I don't know what you want as an example. What do you want, a sphere?
Some field.
Okay, for sphere, everything collapses to nothing. So, okay, we will see. Just have some patience. Okay. It's a very non-trivial subject. It's a subject where you don't write down examples. You try to understand phenomena. Okay? I purposely have not given an example. Okay. So now I want to, and I think you'll be a little bit happier with what I'm going to talk about now, consequences of studying holonomy. But don't forget what holonomy is. And this is a little bit his point. Holonomy is you take closed loops at a base point. You take closed loops at the base point and take a tangent vector at the base point, parallel transport around the closed loop. That is an isometry of the metric, of course, but it's a new vector, right? So you get in fact, you do that for every vector here. You get a linear map. That is each loop gives you a linear map, right? And you get a group at each base point, and it doesn't depend on the base point because it's the usual homotopy discussion. You can just, okay? So you have holonomy of the loops. So now I will write H O L of M and I'm going to have a metric. Okay? And maybe I should put the base point here, P, 0, yeah, equals the set is the group of transformations, linear transformations defined by closed loops starting at P0. Okay? I don't need to write that down, do I? I mean, it's completely clear. All right? Now, this, you see, is a curvature invariant. Curvature a la Riemann, or Gauss, is you take, and let's be very careful to get this thing right. piecewise smooth. The author, Mr. Lee, is not our Mr. Lee, it's a different Mr. Lee. Professor Lee in the United States is very careful to do a lot of his work with piecewise smooth. And it's completely clear that you need to have piecewise smooth here because you have to have concatenation of loops. You have to be able to put two loops together to discuss this matter, right? But you do not need continuous loops. You don't need to go in like you only need piecewise smooth. Okay.
Why not piecewise continuous?
Hmm?
Why not piecewise continuous?
Because obviously I want to do something called parallel transport. And I can only do parallel transport along smooth curve. But if I go along a smooth curve and come to a place where I have to go off to another direction, I have the initial value of the parallel transport there, and I can go off the other direction.
Yes.
That is precisely what I do with the parallelogram business, getting curvature. So you can see this thing is a curvature object. This object is this reflects curvature. This reflects curvature. Okay? And one of the Cartan introduced this. Edi Cartan introduced this thing. And his idea was curvature is too complicated. Sandeep's point, I can't answer your question. You cannot compute random curvature of random things. It's impossible. Okay? So you want to look at something derived from the curvature. Some child of the curvature. Right? And hope that that gives you interesting information. Cartan was an incredible genius to understand that this holonomy was the key object for that. Okay? So this holonomy I'll carry the notation a little bit, is contained in the orthogonal group of the tangent space equipped with a metric at G. That's just notation. You understand what I mean, the orthogonal group? It means the group of isometries with respect to the given structure, GP, of the tangent space. This is what it's contained in. So it is a subgroup of this thing. Now, it's very interesting that Cartan had all of these ideas, I think at latest in 1920, and probably before. And we now know, a professor in Münster, we were talking to Colin about possibly thinking about studying in Münster as a graduate program. Might be a nice place. A very wonderful professor, young professor from Media, named Wilking. In Münster. Now, gave examples and structure of holonomy group in the Riemannian case, which are not closed. Of the orthogonal group. So you can imagine that's an orthogonal group. You understand? I don't know, you have no experience with groups. So the group of orthogonal transformations of a metric, I mean, positive definite bilinear form, is compact. You understand that? I think you can understand it because if you look at this equation, A in matrices, yes, that's the equation for being orthogonal, right? And that, you write down what that looks like in matrices, and you see that with a little thought, that the orthogonal group, if you write A equals Aij, right? And you look at the standard, okay, so you look what this really means for these things, and you write down a norm, and you see that the thing is right, trace is a very good norm of this, okay? Trace norm of this thing. It's the standard norm of the AIJs, okay? You understand, you take the matrix, take 8 times 8, okay? The good norm is trace of this. And since it's equal to the identity, trace of this for every orthogonal matrix is n. Right? So, and trace of A times A transpose is exactly sum of AIJs. Right? So the defining nature of the matrices puts these things in the unit sphere, basically. Okay? So orthogonal group is a compact thing. But so you might have hope that this guy here is going to be a compact thing in this group here, but it may not. Looking gives examples and structure of where it is not. Okay? By the way, that's maybe 2,000 plus minus. So it's not so long. Okay? Now, on the other hand, this contains a subgroup, which is wonderful. So I will start dropping the index. I'm getting tired of this. The holonomy group of M. And I'll write a 0 up here. These are the transformations G gamma for gamma homotopic to the constant map. Okay? So, right? So you can see, even in this case of the parallelogram, here's P0, you can move out a little more, and so on, and so on, and so on, and so on. You're still going to get interesting contributions to the holonomy, right? You're going to see curvature even with an infinitesimal parallelogram. This is one of the ideas of Cartan and Riemann and so on. So this thing, you see, and these are things which are homotopic to the constant map. This is certainly an interesting thing. Okay. Now, when you learn from Professor Penkov that if you have some subgroup, you ought to check out what its relation to the big group. So you have the holonomy group, which have these retractable things, and it's contained in the big group, the big holonomy. The big holonomy, according to recent developments of Burchard Wilking in Münster, the big holonomy is not even close, it's horrible. Okay? But this guy, at least, is a heck of a lot better. Because these things are connected to the identity. And now it's very interesting. What is it when you have a group in a subgroup? Let's say this group is a subgroup H of a subgroup G. Okay. The dream situation is when H is a normal subgroup of G, and we can factor it out. So when you have to compute out whether or not this thing is equal to H again. Right? You would like to know that that's somehow a normal subgroup. That means it's really playing a central role in this thing, and check it. Well, if you have something, I got various, okay, so I take G, H, something like that, and now I take an element here, G, let's call it a holonomy element H, and I conjugate it. You get what I'm doing? I'm conjugating a holonomy element that's retractable to the identity, right? Guess what I'm going to do? I'm going to retract it. Yes? Yes? Yes, I'm going to retract it, and I'm going to see that this thing is retractable to the identity. Is it not retractable to the identity? Obviously it's retractable to the identity because when this t goes to 0, that's the identity, and I have g with g inverse, it goes away. Right? So this is still retractable to the identity. So this is still in holonomy 0 of n. So that says holonomy 0 of n is a normal subgroup of holonomy n. Okay? That's great. Let me tell you why that's great. I factor it out. I look at this thing, I look at the full holonomy, and I factor out this normal guy. Okay? So I factored out all the guys that are retractable to the identity. That means what I have left is not things that are not retractable to the identity. Right? That means I have a map from pi 1 to this thing. Right? Because these are the non-homotopic things to the identity. Yes, I see you.
Yeah, could you repeat the last statement?
Yes.
Means?
Yeah. Again, let's go through the whole thing. The big holonomy, everything. Those are all possible curves starting at P1. As you know, the homotopy group is all possible curves starting at a base point. Modulo, those are retractable to the identity. Right? Well, that means I have a map from pi 1. These things are retractable to the identity. So I have a map from pi 1 to this thing. You got it? Yeah. Pi 1 is all curves modulo retractable to the identity. This is just a piece. This is clear. Okay. It's surjective also. Right? Because that's what pi 1 is. Yeah.
But isn't pi 1 all continuous curves? And here we have piecewise smooth.
Yeah, but in fact, we have representatives of, that's a good point, we have smooth representatives. So, I mean, this is a major point, and I'm glad Colin mentioned that. That in differential topology, we have representatives which are at least piecewise smooth. You know, that's one of the things that you always start in differential topology, is to point out that all this algebraic topology with continuous and blah, 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 in differential setting, it works okay for piecewise smooth. Yeah. It's called homotopy approximation. So it's, okay, so you have this fact, and now this is very interesting. This guy here is countable. Right? It's a compact, it's a manifold, a connected manifold. I assume M is commit. So it's countable. So it's usually finite and generated. We usually have something, we understand the generators and so on. So this thing is countable. So that says that the holonomy group is an extension of the restricted holonomy group by a countable thing. That says it's not much bigger. That says what Wilking did, he is really fooling around with a fundamental group in some sense to get something horrible. Okay. I'm going to have to stop in a minute, but I want to maybe make one or two more remarks. making sure I know some history, so I want to tell you what I learned. Okay. So, let G be a Lie group. Here, G is going to be the orthogonal group. That's a beautiful Lie group. It's even compact. Okay? Okay? Let H be a subgroup of G. I mean, for example, the holonomy group. So the holonomy H, for example, this holonomy group is a subgroup of the orthogonal group. Okay? So here, the group H is said to be a Lie group, Lie subgroup, if and only if H is the group generated by X is Lie algebra. You've had a little experience with Lie groups, I think, with K-bar, right? Okay, you know that a Lie group has a tangent space at the identity. You know the tangent space at the identity has a bracket. So it becomes a Lie algebra. You know it has an exponential map very similar to this thing. And you know that if you take the exponential map, you can look at the group generated by the image of the exponential map. And that is the correspondence between Lie algebra and Lie group. Quite often, as you know in the case of a torus, for example, the exponential map is just a projection map onto the torus. The image group could be dense. Right? I mean, I'm not saying anything about that. This image group, this H could be dense. Okay? The group H is said to be a Lie subgroup whenever it corresponds to a Lie algebra, like this. It could be dense, but it means locally it's good, neighborhood of the identity is good, and so on. Okay? So it's a reasonable thing. Theorem. This is what I enjoyed thinking about this morning or this afternoon. It's very interesting. This is a theorem japonese. So this is very Japanese. It's a funny thing because the problem that these Japanese solve is basically Hilbert's fifth problem. Hilbert's fifth problem is in naive terms, when is a topological subgroup of a Lie group a Lie group? When is a topological subgroup of a Lie group a Lie group? That is a fundamental question. Okay. Now there's some American names of people I knew, and one of them quite well, Gleason, Montgomery, and Zippin, do not handle this question. The Japanese who handle this question, people say Yamabe handle this question. yeah, that I need to solve here, Yamabe. And in fact, Yamabe's manuscript is very incomplete. And then a guy I know very well, actually he's still living, he's almost 100 years old, he's fantastic, Kuranishi. But the guy who really put this on a solid foundation and proved something very good here is a Japanese named Goto. So I would give him credit for what I'm going to say. Okay, I haven't said anything yet, but what I'm going to say. Okay. It's important because this is Hilbert's fifth problem in some sense. It's a very small version of Hilbert's fifth problem. So that a topological group subgroup H G of a Lie group G is a Lie group whenever it is arcwise connected.
Arcless connected is the same as path connected?
That's what I mean by that, yeah. Okay. This is Goto's version of what they're calling Yamabe's theorem, which is in some sense Hilbert's fifth problem solved.
What's the topological subgroup?
Hmm?
What is a topological subgroup? What is topological prefix? Topological.
Well, yeah, it has the induced, it's just a subgroup with the induced topology. So you're putting a topology on it, but I mean, you have to know what the notion is of a continuous path. So in that topology, right? Okay. And here, it's completely obvious, really, because these things are constructed with paths. Yeah? It's here that the corollary of this theorem is that pole 0 is a Lie subgroup of the orthogonal group. Okay. Now I will stop for the day, but I want to make one more remark. You get to this point, and you need some interesting theorems. And another good friend of mine, Borel, Armand Borel, maybe thinking of the Swiss Borel, who, you know, the probability Borel, Borel-Cantelli lemma, things like that. I don't mean that. I mean Armand Borel of modern algebraic groups and so on. Armand Borel proved with a wonderful French mathematician with a Polish name, Ricci, proved that this thing is closed. That is a big deal because there are not many closed subgroups of an orthogonal group. You can imagine if I allow going all over and it's not closed, there are all sorts of things. So we're coming close. You may not like this as an answer, but we're coming close to saying what are all holonomy groups. So in some sense, and then I will give you examples of various manifolds with various holonomy groups, and you might be starting to get happy. Right? And I will give you examples which have certain Ricci curvature, examples which have certain sectional curvature, etc., etc., etc. Okay? But the guideline is holonomy. The guideline is what this holonomy is going to look like. And here's the first guideline. This is theorem of Borel. It's a theorem about compact groups. It is a theorem that I could prove, that even I could prove. And I lock myself in a closet and I prove it in one day. So it's not deep if I could do that. So I just did a scratch paper proof, and then look what Borel did. It's the same thing. It's obvious. It's just obvious. So that's not deep. But this theorem of this this theorem here, and I looked at Goto's proof this afternoon, and it's not as bad as I thought. Okay, so, but we're coming close to very hard problems here. Okay? Good. So let's make a break. How long do you want to take a break?